example 3 in one-dimensional motion, I have a ball tossed upward at 60 meters per second. I want to know how long it takes to come back down to its original height. So we have a ball. It's tossed upward at 60 meters per second. It's going to come back up. Now, it is doing it in one dimension, but that's really hard to draw, so I'm going to bring it back over to here. Right, and it's coming back down to its original height. Okay, I skipped a couple steps, but we'll start writing the grocery list. And I think I've got it in a little bit different order than what I had before, but that's okay. Let's go back up to our picture and finish filling it in. Acceleration due to gravity, and let's again let up be positive. Okay. In this case, our starting and stopping height are the same, so why not let them be 0? Make our lives easy. Our final velocity, right before it hits the ground, we don't know. We're not given. However, we are given the initial velocity is 60 meters per second. We know the acceleration is negative 10 meters per second squared. And we don't know t. I'm going to write up our constant acceleration equations. Okay, and really quick before we move on, let's look at the question. How long? How long is a question of time? So what I want to know is t. I don't know Vy, and I don't have to know Vy necessarily for this question. Okay, let's see if we can do it without Vy. Let's look at the top of equation. I know y, I know y naught, I know v naught y, and I know the acceleration. So this equation has everything in it except t. Let's see if it'll work for us. Okay, y is 0, y naught is 0, v naught is 60 meters per second upward, so that's a positive 60, and the acceleration is a negative 10, so I pulled the minus sign out in front. There we go. Okay. Now notice, this term and this term both have t's in them and everything else is 0. Therefore, I can divide everything by a t and get rid of this one and one factor of that one. So simplifying, I get 0 equals 60 minus 5t. Moving the 5t to the other side, I get 5t equals 60, so t equals 12 seconds. Now, we're done with this problem at this point. We've found how long does it take. But just because we can, let's find that velocity. How fast is it going right before it hits the ground? So v naught y was 60, a sub y was negative 10, and t is 12. Okay, so that's 60 minus 120, which is negative 60 meters per second. Notice, it's symmetric. It goes up at 60 and it's coming back down at the end at 60. What's changed is the direction. One's positive, the other one's negative. Okay. This is a result directly from the fact that we're ignoring air resistance. If we had air resistance included, it would not be symmetric. But since we are, there it is. Now, if we had known that beforehand, so let's pretend we're back to the beginning, and we're smart enough to remember the fact that Vy is going to be equal to v naught y when we're at the same height, going up to going down, just in the opposite direction. Had I remembered that, I could have gone directly to this equation. Right? I could have plugged in a negative 60 here, a positive 60 there, and a minus 10 times t. Okay, so now I need to solve for t. The first thing I need to do is move this 60 to the other side, which gives me a negative 120 equals negative 10t. Dividing both sides by negative 10 gives me t equals 12 seconds. Okay. Now, what is the advantage of remembering that the velocity will be symmetric around its starting point? Just one's up, one's down. That means I don't have to muck with the first equation. I don't have to worry about the fact that it involves a t squared. There's nothing stopping me from using the lower, potentially simpler equation. That might be an important thing to remember as well.